a concept originating from the Big Bang theory, which posits that the universe began as a singularity and has been spreading out ever since. This expansion challenges the human perception of infinity and finite space, pushing the boundaries of what we understand about the cosmos. The concept of dark matter and dark energy further complicates our grasp, with these unseen forces making up approximately 95% of the total universe, dictating its structure and future evolution. Through the lens of cosmology, the scientific study of the universe's origin, structure, and dynamics, humanity seeks to unravel the mysteries that lie beyond our current understanding. Scientists study the early universe using an array of sophisticated methods and technologies, with the cosmic microwave background radiation being a cornerstone among them. This faint glow, often described as the afterglow of the Big Bang, permeates the cosmos, offering a snapshot of the universe as it existed roughly 380,000 years after its inception, when it had cooled down enough for particles to form atoms and light to travel freely. By analyzing the tiny temperature fluctuations in the CMB, researchers can infer the distribution of matter and energy in the early universe, shedding light on its overall structure and evolution. Telescopes, both ground-based and in space, play a pivotal role in peering further back in time. The Hubble Space Telescope, for example, has captured images of galaxies as they appeared just a few 100 million years after the Big Bang, offering invaluable insights into the formation and evolution of these cosmic structures. The upcoming James Webb Space Telescope promises even deeper looks into the universe's history, potentially observing the first galaxies and stars. Another crucial tool in the cosmological arsenal is computer simulation. With the laws of physics as their foundation, these simulations allow scientists to recreate the conditions of the early universe on remarkable scales, from the formation of the first atoms to the clustering of galaxies into the intricate web that fills the cosmos today. This blend of observational data and theoretical frameworks enables scientists to piece together the history of the universe, paving the way for new discoveries about our cosmic origins and destiny. In the universe, four fundamental forces act as the weavers, shaping the cosmos and everything within it. These forces govern the interactions between particles and underpin the vast complexity of the natural world. First, we have gravity, the most familiar yet weakest of the forces, which governs the attraction between objects with mass. From the fall of an apple to the orbit of planets around stars, gravity's reach is immense, sculpting the structure of the universe on the grandest scales. Next, the electromagnetic force, responsible for the interactions between charged particles. This force allows atoms to bond into molecules, creates the light we see, and powers the electricity and magnetism that are foundational to much of modern technology. The strong nuclear force holds the nucleus of an atom together, overcoming the electromagnetic repulsion between positive protons to bind nucleons in the tight embrace of atomic cores. It is the strongest of the forces, but operates over the shortest range, confined to the nucleus itself. Lastly, the weak nuclear force is responsible for radioactive decay and nuclear reactions that power stars. It plays a crucial role in the nuclear processes that synthesize elements and enable the sun to shine, fueling life on Earth. These forces, each distinct in their reach and power, together weave the intricate fabric of the universe, from the smallest particles to the largest structures in the cosmos. Their interplay and balance are crucial for the structure and evolution of everything we observe, offering a compelling glimpse into the fundamental principles that govern our reality. Particle physics is the branch of science that delves into the realm of the smallest known building blocks of the universe and the forces that govern their interactions. It explores the fundamental particles such as quarks, which combine to form protons and neutrons, leptons, which include electrons and neutrinos, and the carrier particles, or bosons, which mediate the four fundamental forces of nature. This discipline seeks to answer profound questions about the nature and origin of mass, the structure of space and time, and the unification of the forces that shape the cosmos. At the heart of particle physics is the Standard Model, a theory that has been developed over the latter half of the 20th century. It outlines a framework for the electromagnetic, weak, and strong nuclear interactions, successfully explaining a vast array of experimental results and the existence of diverse particles. However, it does not incorporate the gravitational force described by the general theory of relativity, which remains one of the greatest challenges in theoretical physics. Experiments in particle physics often involve accelerators that propel particles to high energies before they are made to collide, briefly producing conditions akin to those just after the Big Bang. Detectors capture the aftermath of these collisions, allowing scientists to study the properties of particles and forces at play. Facilities like the Large Hadron Collider, also known as the LHC at CERN, have been instrumental in landmark discoveries, including the Higgs boson, which provides a mechanism for particles to acquire mass. Despite its successes, many questions remain unanswered, and the quest for a deeper understanding continues, driving the exploration of phenomena beyond the standard models such as dark matter, supersymmetry, and the grand unification of forces. Through particle physics, we inch closer to comprehending the fundamental principles that govern the universe, revealing the exquisite architecture of the cosmos on its most fundamental level. Particle physics offers a foundational lens through which the complexities of the universe can be understood, explaining not just what the universe is made of, but also how it works at its most fundamental level. At the heart of this exploration is the standard model of particle physics, a robust theory that categorizes all known fundamental particles into quarks, leptons, and bosons, and describes three of the four fundamental forces, omitting gravity. Through the standard model, scientists can explain a plethora of phenomena, from the behavior of atoms to the processes powering the sun and other stars. One of the most significant contributions of particle physics to our understanding of the universe is the explanation of the origin of mass. The Higgs boson, sometimes called the God particle, discovered in 2012 at the Large Hadron Collider, interacts with other particles to give them mass, a phenomenon without which the universe would be a very different place, unable to form atoms, molecules, or anything else. Particle physics dives into the early universe, providing insights into moments fractions of a second after the Big Bang, where temperatures and energies were so high that the four fundamental forces were unified. Investigating these extreme conditions, particle physicists explore symmetry breaking, a process that might explain how these forces acquired their distinct characteristics as the universe cooled and expanded. While the standard model has been remarkably successful, it doesn't encompass everything. It doesn't include gravity, accounted for by general relativity, and it doesn't explain dark matter and dark energy, which make up about 95% of the total content of the universe. Therefore, particle physics is not just a story of triumph, but also a narrative of the unknown, driving the search for a more complete theory of everything that can explain not just the world of the very small, but the cosmos in all its vast complexity. The Big Bang Theory is the prevailing cosmological model that describes the early development and current expansion of the universe. According to this theory, the universe originated from an extremely hot and dense singularity approximately 13.8 billion years ago. This singularity then began expanding and cooling, leading to the formation of subatomic particles and simple atoms. As the universe continued to expand and cool, gravity caused matter to coalesce into stars, galaxies, and larger structures. A pivotal piece of evidence supporting the Big Bang theory is the observation of the cosmic microwave background radiation. This is the afterglow of the initial explosion, a faint cosmic background radiation permeating the universe and providing a snapshot of the infant universe, about 380,000 years after the Big Bang. The distribution of galaxies and their redshift, observed as they move away from us, indicating the universe's expansion, is another cornerstone that corroborates this theory. Despite its name, the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. This insight led to a deeper understanding of the universe's dynamics, including the realization that its fate is tied to the density of matter and energy it contains. The Big Bang theory doesn't explain what preceded the singularity or the cause of the expansion, leaving ample room for speculation and further study in cosmology. Its elegance lies in its ability to unify a wide array of astronomical observations into a coherent framework of the universe's evolution, from a hot, dense state to the vast, complex cosmos we observe today. The Big Bang led to the universe's expansion through an initial rapid inflation, a concept that bridges the gap between the singularity and the large, structured cosmos we observe today. Unlike an explosion in a pre-existing space, the Big Bang marked the simultaneous creation and expansion of space itself. In the first infinitesimal fractions of a second, the universe expanded exponentially from a point of nearly infinite density and temperature to a vastly larger size. This rapid inflationary period laid down the large-scale structure of the universe, stretching out any initial irregularities and leaving the universe remarkably smooth and homogeneous on a large scale. As the universe expanded, it cooled, allowing energy to be converted into various subatomic particles, including electrons, neutrons, and protons, in processes detailed by the Standard Model of particle physics. These particles eventually combined to form hydrogen and helium atoms in a process known as nucleosynthesis. The universe's expansion continued at a slower pace after inflation, driven by the momentum of the initial expansion and the ongoing repulsive effect of dark energy, a mysterious force that accelerates the universe's expansion. Gravity played an essential role in the post-inflation universe, causing regions slightly denser than their surroundings to collapse under their own gravity, forming stars, galaxies, and larger structures in the cosmos. This ongoing interplay between expansion and gravity shapes the universe's structure and evolution. The universe's expansion, observable through the red shift of light from distant galaxies, continues to this day as galaxies move away from each other in the ever-growing cosmic expanse. This expansion is a direct consequence of the Big Bang, highlighting the dynamic and evolving nature of the universe. The Big Bang theory, foundational to modern cosmology, is supported by several key pieces of evidence that together present a compelling case for the universe's hot, dense origin and its subsequent expansion. Firstly, the cosmic microwave background radiation serves as a crucial pillar supporting the Big Bang theory. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is a faint glow of radiation that fills the universe, acting as a relic of its hot, dense infancy. This radiation is remarkably uniform in all directions, but detailed observations have revealed tiny fluctuations that correspond to the early distribution of matter in the universe. The CMB directly indicates the universe's state approximately 380,000 years after the Big Bang, when it had cooled sufficiently for electrons and protons to combine into neutral atoms, allowing light to travel freely. Another line of evidence comes from the observation of the universe's expansion. Edwin Hubble, in 1929, observed that distant galaxies are moving away from us with their speed proportional to their distance. This redshift of galaxies' light is consistent with a universe that has been expanding from an initially hot, dense state. If the universe is expanding, it must have been smaller, hotter, and denser in the past, as predicted by the Big Bang theory. Additionally, the abundance of light elements provides corroborative evidence for the Big Bang. The theory predicts that in the first few minutes after the Big Bang, conditions were ripe for nuclear fusion, leading to the formation of hydrogen, helium, and trace amounts of lithium in proportions that depend on the density of the universe at that time. Observations of the relative abundances of these light elements in the oldest stars and in interstellar space match the predictions of Big Bang nucleosynthesis remarkably well. These pieces of evidence, the cosmic microwave background radiation, the expansion of the universe observed through the redshift of galaxies, and the abundance of light elements, are considered the foundational pillars that support the Big Bang theory. Together, they offer a consistent and comprehensive explanation for the universe's origin, its evolution over 13.8 billion years, and its current structure and composition. The conditions right after the Big Bang were unfathomably hot and dense, unlike anything we can directly observe today. Initially, the universe was in a state where temperatures were so high that particles of matter and antiparticles of antimatter were being created and annihilated in equal measures. This extreme energetic phase meant that the universe was filled with a quark-gluon plasma, a state of matter where quarks, which typically make up protons and neutrons, and gluons, particles that carry the strong force which binds quarks together, were free and not confined within particles like protons and neutrons. As the universe expanded, it cooled rapidly, crossing various threshold temperatures that led to significant changes in its composition. Approximately 1 microsecond after the Big Bang, the universe cooled enough for quarks and gluons to combine into protons and neutrons. Several minutes into the expansion, the universe had cooled further to allow protons and neutrons to start forming simple nuclei in a period known as Big Bang nucleosynthesis. This primarily produced isotopes of hydrogen, helium, and traces of lithium and beryllium, setting the stage for the chemical composition of the cosmos. For the next few 100,000 years, the universe continued to cool and expand, with photons, particles of light, being constantly scattered by the free electrons in a fog. Around 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin, allowing electrons to combine with nuclei to form the first neutral atoms, a process known as recombination. This liberation of photons, now no longer scattered by free electrons, gave rise to the cosmic microwave background radiation, a snapshot of the universe at that moment and now observable as a faint glow permeating the cosmos. This era, following the chaotic hot conditions of the immediate aftermath of the Big Bang, set the foundation for the evolution of the complex universe we observe today, with its vast structures of galaxies, stars, and planets formed from the primordial elements created in these initial moments. Immediately after the Big Bang, the universe was a seething, hot, dense state where the energy levels were so high that particles and their antiparticles were being continuously created and annihilated. The very first particles to exist in these moments are believed to be quarks, leptons, such as electrons, and their respective antiparticles, along with bosons, which are force-carrying particles. During this epoch, known as the quark epoch, the universe was too hot and dense for quarks to bind together into protons and neutrons. Instead, quarks and gluons, the bosons that mediate the strong force, existed in a free state, in what is called a quark-gluon plasma. As the universe expanded and cooled, the energy of the universe fell to a point where quarks could finally combine to form protons and neutrons in a process known as hadronization. Electrons, being one of the types of leptons, were also present from these earliest moments. However, the universe was too energetic for them to form atoms by combining with protons. This capability would come later, as the universe cooled further. During the earliest moments, neutrinos, another type of lepton, were also abundantly produced. Neutrinos interact very weakly with other matter, and shortly after their creation, they decoupled from other particles and began to stream freely through space, creating a cosmic neutrino background similar to the cosmic microwave background radiation, but even more elusive and difficult to detect. These first particles, formed in the immediate aftermath of the Big Bang, were the building blocks for all the complex structures we observe in the universe today. Their interactions, governed by the fundamental forces of nature, led to the cosmos evolving from a uniform soup of primordial particles into a rich tapestry of galaxies, stars, and planets. A fraction of a second after the Big Bang, the universe was in an extremely hot, dense phase beyond current physics' complete understanding. This period is known as the Planck era, named after Max Planck, the founder of quantum theory. It lasted from 0 to approximately 10 to the negative 43rd seconds after the Big Bang, during which the universe's temperature was so high that the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely unified into one fundamental force. The energy scales at this time were so extreme that current physical theories, including general relativity and quantum mechanics, are insufficient to describe conditions accurately. Immediately following the Planck era, the universe entered the grand unification epoch, which lasted until around 10 to the negative 36th seconds. During this period, temperatures dropped just enough for the gravitational force to separate from the other forces, marking the first step in the differentiation of the fundamental forces. This epoch might have also featured a phase of rapid inflation, where the universe expanded exponentially in a very short time frame. Inflation theory suggests the universe increased its size by a factor of at least 10 to the 26th, smoothing out any irregularities and setting the stage for a homogeneous and isotropic cosmos on large scales. By 10 to the negative 32nd seconds, as the universe continued to cool and expand, the strong nuclear force became distinct from the electroweak force, the combined electromagnetic and weak nuclear forces. The universe was still in a plasma state, filled with a hot, dense soup of quarks, leptons, such as electrons and neutrinos, and their antiparticles, along with various force-carrying particles like photons and gluons. These conditions were so extreme that particles were continuously being created and annihilated. This fractional moment in time after the Big Bang set the initial conditions for everything that followed, laying down the fundamental properties and distribution of matter and energy that would eventually lead to the formation of atoms, stars, galaxies, and the larger cosmic structures observed in the universe today. The complexity and diversity of the cosmos all trace back to this brief initial burst of expansion and cooling, a testament to the power of the initial conditions set in the universe's first moments. Cosmic inflation is a theory proposed to explain the very early growth of the universe, positing a period of extremely rapid, exponential expansion within the first tiny fraction of a second after the Big Bang. According to this theory, the universe increased in size by a factor of at least 10 to the 26th in less than 10 to the negative 32nd seconds. This dramatic increase solved several long-standing puzzles of the Big Bang theory, such as the horizon problem, the flatness problem, and the magnetic monopole problem, by providing a mechanism that made the observable universe homogeneous and isotropic, the same in all directions, and spatially flat to an extraordinary degree. Inflation is thought to have been driven by a hypothetical field known as the inflaton field, which permeated space. This field had properties that would cause space itself to expand exponentially if it were in a particular high-energy state. As the inflaton field decayed to a lower energy state, this rapid expansion slowed down, and the energy stored in the field was released in a process called reheating. This reheating filled the universe with the hot, dense plasma of particles that we associate with the more traditional picture of the Big Bang. Evidence supporting cosmic inflation comes from observations of the cosmic microwave background radiation, which shows slight variations, anisotropies, in temperature. These tiny fluctuations, which are incredibly uniform across the sky, match the predictions made by inflation theory about the distribution of matter and energy in the early universe. Inflation predicts that these fluctuations should be almost the same at all scales, a prediction that has been confirmed by detailed mapping of the CMB by various space-based observatories. Cosmic inflation represents a crucial bridge between the mystery of the universe's initial state and the Big Bang nucleosynthesis and later structure formation. It's an integral part of our current understanding of cosmology, providing a compelling framework for explaining how a uniform, dense point could evolve into the vast, structured cosmos we see today. Cosmic inflation profoundly shaped the early universe, setting the stage for the development of cosmic structures and solving several major cosmological puzzles. This rapid expansion occurred within the tiniest fraction of a second after the Big Bang, during which the universe grew exponentially, stretching far beyond the subatomic scales to macroscopic scales in a blink of an eye. This dramatic event had multiple lasting effects on the cosmos. One of the most striking features of the universe is its uniformity on large scales. Despite the clumps of galaxies and vast voids that pepper the cosmos, the overall density of matter and energy and the background temperature are remarkably even across vast distances. Cosmic inflation smoothed out any initial irregularities in the density of the early universe, promoting a uniform distribution of matter and energy evidenced by the uniform temperature of the cosmic microwave background radiation across the sky. Inflation also addressed the flatness problem, the observation that the universe appears to be spatially flat. The theory of general relativity allows for a universe that is spatially open, closed, or flat, contingent upon the average density of matter and energy in the universe. Inflation stretched the space itself so vastly that any initial curvature of the universe would now appear flat, much like how the surface of the Earth seems flat over small distances despite its overall spherical shape. The quantum fluctuations in the inflaton field during inflation were stretched to cosmic scales, seeding the slight variations in density that would later grow under the influence of gravity to form galaxies, stars, and other large-scale structures. These initial perturbations were imprinted in the cosmic microwave background and have been meticulously mapped, confirming predictions made by inflation. Theoretical predictions based on the conditions of the early universe suggested the formation of various exotic particles and defects in space, such as magnetic monopoles. These have not been observed, which puzzled scientists. Inflation diluted the concentration of any such exotic particles or defects to negligible levels, thus explaining their absence or rarity in the present universe. Cosmic inflation proposes a period of transformation that elegantly explains these and other aspects of the cosmos, making it a cornerstone of modern cosmological theories. The rapid expansion effectively set initial conditions from which the structured, dynamic, and complex universe we observe today could evolve. The quark epoch represents a stage in the early universe following the Planck epoch, existing roughly from 10 to the negative 12th seconds to 10 to the negative 6th seconds after the Big Bang. During this era, the universe was filled with a hot, dense soup known as a quark-gluon plasma. Temperatures were so extreme, ranging from about 10 to the 12th power to 10 to the 15th power Kelvin, that quarks, fundamental particles that make up protons and neutrons, could not bind together due to the high energy levels, instead existing in a free state alongside their force carrier particles, gluons. This epoch was characterized by a universe still too hot and too dense for the formation of atomic nuclei, let alone atoms. The predominant interactions were among quarks, gluons, leptons, such as electrons and neutrinos, and their respective antiparticles, with these particles being continuously created and annihilated in pairs. During this time, the four fundamental forces had already taken on their separate identities. Gravity had split from the other forces during the grand unification epoch that preceded the quark epoch, and the strong, weak, and electromagnetic forces operated as distinct entities. As the universe expanded and cooled, the energy density dropped, eventually reaching a point where it was no longer sufficient to break apart the bonds that would form between quarks. This transition marked the end of the quark epoch and the beginning of the hadron epoch, during which quarks combined to form protons and neutrons, collectively known as hadrons. This critical phase set the stage for the subsequent epochs of cosmic evolution, leading towards the synthesis of simple atomic nuclei and the formation of neutral atoms, setting the foundational blocks for the chemical elements that would fill the universe. During the infancy of the universe, a period known as the Big Bang, temperature and density conditions underwent dramatic changes that are foundational to our understanding of cosmology today. Initially, right after the Big Bang, believed to have occurred around 13.8 billion years ago, the universe was in a state of extreme heat and density, far beyond anything we experience or can recreate on Earth. Temperatures soared to billions of degrees, a condition allowing the four fundamental forces of nature to be unified. As the universe expanded, a process that continues today but at a much slower rate, it cooled significantly. Within the first few minutes, the temperature dropped sufficiently to allow protons and neutrons to form the first simple nuclei, an epoch known as nucleosynthesis. This cooling and expansion over hundreds of thousands of years eventually allowed electrons to combine with nuclei to form atoms, predominantly hydrogen and helium, marking the transition from a plasma state to the gas state. This phase set the stage for the formation of stars and galaxies, sculpting the universe's structure as we observe today. The intricate dance between temperature and density during the universe's early moments highlights an extraordinary period of transformation, pivotal in creating the cosmos we inhabit. Quarks are fundamental particles that serve as the building blocks of matter in the universe, discovered in the 1960s through a series of particle accelerator experiments. Unlike atoms, which were once considered the smallest components of matter, quarks are truly elementary, with no structure or components beneath them, according to current scientific understanding. They are key constituents of hadrons, which include protons and neutrons, the particles that, along with electrons, form atoms. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom, each possessing unique properties. For example, a proton is composed of 2 up quarks and 1 down quark, while a neutron consists of 1 up quark and 2 down quarks. One of the most intriguing aspects of quarks is the force that holds them together, the strong nuclear force, mediated by particles known as gluons. This force is so powerful that it effectively confines quarks within hadrons. They cannot exist independently but are always found in combination. This phenomenon, known as quark confinement, challenges scientists' ability to directly observe individual quarks, with their presence and properties inferred from high-energy experiments. The study of quarks not only deepens our understanding of the microscopic fabric of the universe, but also sheds light on the early moments following the Big Bang, where these fundamental particles played a critical role in the formation of matter as we know it. Through ongoing research in particle physics, scientists continue to explore the complexities of quarks, aiming to unravel more about the universe's fundamental nature and its origins. In the early universe, the formation of quarks was a pivotal event that occurred shortly after the Big Bang, during a period known as the quark epoch. This epoch took place approximately 10 to the power of -12 seconds, 1/trillionth of a second, after the universe began to expand, and is characterized by the universe being filled with a hot, dense soup of quarks, gluons, and other elementary particles. At this stage, the temperature of the universe was unimaginably high, on the order of 10 to the power 12 Kelvin, a condition allowing quarks and gluons to exist freely in what is termed a quark-gluon plasma. As the universe expanded, it cooled rapidly, leading to crucial changes in the state of matter. During the cooling process, as temperatures fell below a critical threshold, quarks started to combine together due to the strong nuclear force, which is the most powerful of the 4 fundamental forces at these short distances. This force is mediated by gluons, effectively acting as glue holding quarks together. Initially, quarks formed pairs or triplets, leading to the creation of more complex particles such as protons and neutrons, which are trios of up and down quarks. This binding of quarks marked the end of the quark epoch and the beginning of the hadron epoch, during which the universe was filled predominantly by protons and neutrons. This transition from freely roaming quarks to bound states within protons and neutrons was a critical step in the evolution of the universe, setting the stage for the formation of atoms, stars, and eventually galaxies. The processes that governed the formation and behavior of quarks in the early universe remain a subject of intense study in particle physics and cosmology, offering glimpses into the forces and conditions that shaped the cosmos. Antiquarks are the antimatter counterparts to quarks, the fundamental building blocks that compose matter in the universe. Just as antimatter generalizes the concept of opposite counterparts to matter particles, antiquarks mirror quarks in charge and other quantum properties, yet they possess exact opposite values. This means that for each of the 6 flavors of quarks, up, down, charm, strange, top, and bottom, there exists a corresponding antiquark with the same mass but opposite electric charge, color charge, and other quantum numbers. An interesting facet of antiquarks is their role in the annihilation process. When a quark encounters its corresponding antiquark, they can annihilate each other, releasing energy in the form of high-energy photons or other particles. This phenomenon underlines the symmetry in the universe between matter and antimatter, although intriguingly, the observable universe today appears to be dominated by matter. The existence of antiquarks is not just theoretical, they have been produced and observed in high-energy particle collisions, such as those conducted in particle accelerators. These experiments recreate the high-energy conditions similar to those in the early universe, allowing physicists to study the properties of quarks and antiquarks, as well as the strong force that governs their interactions. Understanding antiquarks is crucial for theoretical and experimental particle physics, contributing to our comprehension of the fundamental principles that govern matter and antimatter. Their study not only enriches our knowledge of the universe's microscopic building blocks, but also provides insights into the asymmetry between matter and antimatter, a central puzzle in cosmology concerning why the universe is composed predominantly of matter today. Quarks and antiquarks interact through the strong nuclear force, one of the four fundamental forces of nature, which is mediated by particles known as gluons. This force is characterized by its immense strength, allowing it to bind quarks together to form protons, neutrons, and other particles, despite the repulsion between quarks of like charges. The interaction between quarks, whether they are matter or antimatter, is governed by the exchange of gluons in a unique manner described by the theory of quantum chromodynamics. Each quark carries a property known as color charge, analogous to electric charge in electromagnetism. But instead of being positive or negative, the color charge comes in three types: red, green, and blue, as well as their corresponding anticolors for antiquarks. Gluons, which carry the strong force, also carry a combination of color and anticolor charge, allowing them to act as the exchange particles between quarks and antiquarks. When a gluon is exchanged between a quark and an antiquark, it can change the color charge of the involved particles, ensuring that the color charge is conserved in the process. One of the most fascinating aspects of quark-antiquark interaction is the phenomenon of confinement. Unlike electromagnetic force, the strong force does not diminish as quarks move farther apart. It remains constant or even increases, effectively confining quarks and antiquarks within hadrons, particles made of quarks such as protons and neutrons. This is why quarks and antiquarks cannot be found in isolation, but are always bound together in composite particles. When a quark encounters an antiquark of the corresponding anticolor, they can annihilate each other, leading to the conversion of their mass into energy, typically in the form of high-energy photons or other particle-antiparticle pairs. This interaction, while highlighting the destructiveness of meeting between matter and antimatter, also underscores the rich tapestry of forces and particles that constitute the fundamental fabric of the universe. Through these interactions, quarks and antiquarks play a crucial role in the structure and dynamics of matter at the most fundamental level. The strong nuclear force, one of the universe's four fundamental forces, played a pivotal role in the early stages of particle formation following the Big Bang. This force is responsible for holding quarks together to form protons, neutrons, and other hadrons, and it governs the interactions between these particles to produce the nuclei of atoms. In the extremely high temperatures and densities that characterized the initial moments of the universe, the strong force was crucial in transitioning from a quark-gluon plasma, a state in which quarks and gluons were unbound and roamed freely, into a phase where quarks began to coalesce into the composite particles that constitute the matter we observe today. During the first microseconds after the Big Bang, the universe began to cool from its initial, extraordinarily high temperatures. As it cooled, the strong force began to assert itself, causing quarks to bind together to form protons and neutrons, a process known as hadronization. This was a critical step in the formation of matter, as protons and neutrons are the building blocks of atomic nuclei. The strong force ensured that these particles remained bound together despite the high kinetic energy that would typically pull similarly charged particles apart. Subsequently, as the universe continued to expand and cool, protons and neutrons started to combine under the influence of the strong force to form the nuclei of the simplest elements, such as hydrogen, helium, and traces of lithium, through the process of nucleosynthesis. This period marked the universe's transition from a particle soup, dominated by individual quarks and gluons, to one in which matter began to take on a more familiar form, setting the stage for the formation of atoms, molecules, stars, and galaxies. The strong force, with its unique properties of confinement and asymptotic freedom, meaning it becomes stronger as quarks move apart and weaker as they come closer together, was essential not just for the cohesion of quarks into composite particles, but also for the synthesis of the early nuclei. Without the strong force, the universe would have remained a diffuse cloud of unbound quarks and leptons without the complexity and structure we observe today. Through its role in early particle formation, the strong force was instrumental in shaping the universe's evolution from the first moments after the Big Bang. Quantum fluctuations are a fundamental phenomenon arising from the principles of quantum mechanics, particularly the uncertainty principle proposed by Werner Heisenberg. This principle suggests that it is impossible to simultaneously know both the exact position and momentum of a particle, leading to the idea that the vacuum of space is not empty, but teems with activity. In this vacuum state, particles and antiparticles spontaneously appear and disappear over incredibly short timescales. These temporary particles are known as virtual particles. The concept of quantum fluctuations is crucial for understanding the fabric of the universe at its most fundamental level. Unlike the classical view of a vacuum as completely empty space, quantum mechanics reveals a dynamic and bustling realm where particles such as quarks and electrons, along with their corresponding antiparticles, can momentarily pop into existence from seemingly nothing before annihilating each other and vanishing. This process is governed by the energy-time version of the uncertainty principle, which allows for the temporary violation of energy conservation, provided that the violation does not last long enough to be observed directly. Quantum fluctuations have profound implications for various areas of physics, including cosmology and particle physics. They are thought to have played a significant role in the early universe, seeding the formation of cosmic structure. Tiny fluctuations in the density of matter in the early universe, amplified over billions of years by gravitational attraction, led to the complex structures we observe today, such as galaxies and galaxy clusters. Additionally, these fluctuations are integral to the Casimir effect, a phenomenon where two closely placed metal plates attract each other due to the differential pressures of quantum vacuum fluctuations inside and outside the gap between the plates. Quantum fluctuations underscore the non-intuitive nature of the quantum world, where the very fabric of reality defies classical expectations and reveals a universe that is dynamic, even in its most seemingly empty spaces. Quantum fluctuations played a crucial role in shaping the large-scale structure of the early universe. During the period of cosmic inflation, a rapid expansion of the universe that is believed to have occurred fractions of a second after the Big Bang, these subatomic fluctuations were stretched to macroscopic scales. As the universe expanded, regions that were slightly denser than their surroundings due to quantum fluctuations began to attract more matter under the influence of gravity. This process gradually magnified the initial tiny irregularities into the vast cosmic web of galaxies and galaxy clusters we observe today. The inflationary model predicts that these quantum fluctuations are the seeds for the temperature variations in the cosmic microwave background radiation, the afterglow of the Big Bang, which provides a snapshot of the universe around 380,000 years after its inception. Observations of the CMB by satellites such as COBE, WMAP, and Planck have revealed tiny temperature fluctuations consistent with the predictions of quantum theory and inflation. These fluctuations correspond to regions of slightly different densities, supporting the idea that quantum fluctuations in the early universe laid down the foundational blueprint for the formation of cosmic structures. Moreover, the influence of quantum fluctuations during inflation implies that the properties of the universe on the largest scales are determined by events at the quantum level, bridging the realms of quantum mechanics and general relativity. This interplay between the smallest and the largest scales in the universe is a profound demonstration of how quantum fluctuations during the universe's earliest moments have left an indelible mark on the structure of the cosmos, influencing the distribution of galaxies and the evolution of the universe itself. Yes, Quantum fluctuations can indeed lead to the creation of particles, a fascinating phenomenon grounded in the principles of quantum field theory. According to this theory, even what we consider a vacuum in space is not empty, but filled with fluctuating fields representing each type of particle. These fluctuations can momentarily create pairs of particles and antiparticles out of nothing, as long as they respect the Heisenberg uncertainty principle, which allows for the temporary emergence of energy in the form of particles, so long as it disappears quickly enough not to violate energy conservation laws over observable timescales. This process is exemplified by the creation of virtual particles, which are particle-antiparticle pairs that pop into existence and then annihilate each other. While these particles cannot be directly observed because of their ephemeral nature, their indirect effects can be detected and have significant physical consequences. One of the most notable examples of such an effect is the Hawking radiation around black holes. According to Stephen Hawking's groundbreaking theory, quantum fluctuations near the event horizon of a black hole can result in one particle of the pair being captured by the black hole, while the other escapes as radiation, leading to the black hole losing mass over time. Similarly, the Casimir effect showcases how quantum fluctuations can generate a measurable force between two uncharged parallel plates placed very close to each other in a vacuum. The energy density of virtual particles fluctuates between the plates and outside them, giving rise to a pressure that pushes the plates together. This is a direct consequence of the limitations on the wavelengths of virtual particles that can exist between the plates, compared to those that can exist outside, which modifies the energy of the vacuum in these regions. Thus, quantum fluctuations do more than just create particles. They underscore the dynamic nature of the quantum vacuum and reveal the profound connections between the forces governing the universe at both the microscopic and cosmic scales. Quantum fluctuations play an indirect yet crucial role in the formation of protons, connecting the foundational principles of quantum mechanics with the complex structures of the standard model of particle physics. Protons are composite particles consisting of three quarks, two up quarks and one down quark, held together by the strong nuclear force mediated by gluons. The story of proton formation, influenced by quantum fluctuations, begins in the early universe, shortly after the Big Bang. During the quark epoch, the universe was dense and energetic enough for quarks, gluons, and their corresponding antiparticles to be freely produced from the energy present, thanks to quantum fluctuations. These fluctuations are transitions in energy levels within quantum fields that can momentarily create particle-antiparticle pairs. In the intense heat of the early universe, this meant a soup of quarks, antiquarks, and gluons constantly popping into and out of existence. As the universe expanded and cooled, it reached a point where it was no longer hot or dense enough to sustain these fluctuations in a way that allowed quarks and antiquarks to exist freely. The surviving quarks began to coalesce, forming stable combinations due to the strong force. This force, governed by quantum chromodynamics, thrives on the energy from these quantum fluctuations, harnessing it to bind quarks into protons and neutrons. This quantum aspect underscores the non-intuitive fact that even what we consider the vacuum of space is a bubbling cauldron of potential energy capable of influencing the formation of matter. The protons formed in this early epoch have remained stable over billions of years, eventually becoming part of the atomic nuclei that make up the chemical elements of the universe. The indirect influence of quantum fluctuations on this process illustrates the interconnectedness of quantum mechanics and particle physics, showing how the laws governing the smallest scales of the universe impact the structure and stability of matter across cosmic timescales. The cooling of the universe is fundamentally tied to its expansion, a process that began with the Big Bang approximately 13.8 billion years ago. According to cosmological theories, the initial state of the universe was an extremely hot, dense point. As it expanded, the space between the particles within it also grew, causing the energy density and temperature to decrease over time. This cooling process can be somewhat analogically understood by considering how gases behave in thermodynamics. When a gas expands, it does work against its surroundings, and loses energy in the process, leading to a decrease in temperature. In the case of the universe, as space itself expanded, the wavelength of the radiation filling the universe stretched as well. This stretching of wavelengths corresponds to a shift towards the red end of the electromagnetic spectrum, which signifies a decrease in energy or cooling. During the first few moments after the Big Bang, the universe was so hot that particles of matter and antimatter were being created and annihilated in pairs. However, as the universe expanded and cooled, it eventually reached a temperature where these high-energy processes could no longer occur, leading to a predominance of matter over antimatter and the formation of stable particles like protons and electrons. This period of cooling also allowed for the formation of the first nuclei in a process known as nucleosynthesis, around 3 minutes after the Big Bang, when the universe had cooled enough for protons and neutrons to combine into nuclei without being torn apart. Hundreds of thousands of years later, as the expansion and cooling continued, the universe reached a state where electrons could bind to nuclei to form neutral atoms, leading to the recombination epoch. The cooling of the universe is a pivotal process that has played a critical role in shaping the cosmos as we know it, from facilitating the formation of fundamental particles and structures to enabling the existence of life. This process of cooling, intrinsically linked to the expansion of the universe, has determined the timeline for a series of cosmological milestones that have led to the current state of the universe. Initially, the extremely high temperatures of the early universe prevented the formation of stable matter as we know it. Particles of matter and antimatter were continuously created and annihilated in a high-energy environment. As the universe expanded and cooled, it reached a point where these high-energy processes could no longer occur, leading to the predominance of matter over antimatter and allowing for the formation of stable particles such as protons and neutrons. Further cooling facilitated the epoch of nucleosynthesis, a brief period when the universe had cooled enough for protons and neutrons to combine into the nuclei of the lightest elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. This process laid the foundation for chemical diversity in the universe. Even more significantly, the cooling of the universe led to the recombination epoch, when electrons were able to combine with nuclei to form neutral atoms. This event dramatically reduced the scattering of photons by free electrons, allowing the universe to become transparent for the first time. The photons that were released at this time formed the cosmic microwave background radiation, which provides us with a snapshot of the universe at this early stage and is a crucial piece of evidence for the Big Bang model. On a larger scale, the cooling of the universe set the stage for gravitational forces to condense matter into the first stars and galaxies. These structures further synthesized heavier elements in their cores, contributing to the chemical complexity necessary for planets and, eventually, life to emerge. In essence, the significance of the universe cooling extends from allowing the formation of the first stable particles to enabling the development of complex structures and life. It illustrates a fundamental narrative of transformation and complexity emerging from simplicity, governed by the laws of physics and the initial conditions of the cosmos. The cooling of the universe had a profound effect on particle interactions, fundamentally shaping the transition from a primordial soup of elementary particles to the structured matter that forms the cosmos today. In the extremely hot and dense conditions immediately following the Big Bang, particles had too much energy to bind together, leading to a state where matter existed in a plasma of quarks and leptons, constantly being created and annihilated. As the universe expanded, it cooled, reducing the average energy of particles. This cooling had several key effects on particle interactions. When the universe cooled to below a certain critical temperature, the strong nuclear force could finally overcome the kinetic energy of quarks, allowing them to bind together to form nucleons, protons, and neutrons. This marked the end of the quark epoch and the beginning of the hadron epoch, a significant transition in the organization of matter. The continued cooling of the universe set the stage for nucleosynthesis, the process by which the first atomic nuclei formed. This occurred a few minutes after the Big Bang, when the temperature dropped to the point where protons and neutrons could combine to form the nuclei of the lightest elements without being torn apart by high-energy photons. This era produced primarily hydrogen, helium, and trace amounts of lithium and beryllium. Hundreds of thousands of years post-Big Bang, the universe had cooled enough for electrons to bind to nuclear cores to form neutral atoms. This recombination significantly affected particle interactions by drastically reducing the scattering of photons. As a result, the universe became transparent to radiation, allowing light to travel through space unimpeded. The photons freed during this epoch form the cosmic microwave background radiation, a crucial observational window into the early universe. The cooling of the universe also allowed for the gravitational collapse of matter. Denser regions of matter attracted more particles due to gravitational forces, eventually leading to the formation of stars and galaxies. In these stars, nuclear fusion processes began, synthesizing heavier elements from lighter ones and further enriching the cosmic chemical complexity. Each stage of cooling resulted in a decrease in the kinetic energy of particles, which facilitated new types of interactions based on the various fundamental forces, primarily the strong and electromagnetic forces. This gradual transition shaped the universe's evolution, leading from a uniform hot plasma to a complex, structured cosmos filled with a vast variety of celestial objects and life as we know it. Quarks began to combine into composite particles such as protons and neutrons, known as nucleons, during a period called the Hadron Epoch. This epoch occurred approximately 10 to the power of -6 seconds, 1 microsecond, to 1 second after the Big Bang, when the universe had cooled sufficiently from its initial extremely high temperatures. During the initial moments post-Big Bang, the universe was so hot and dense that quarks couldn't bind together due to the overwhelming kinetic energy that kept them apart. They existed in a state known as the quark-gluon plasma, where quarks, antiquarks, and gluons roamed freely in a soup-like condition. As the universe expanded, it cooled down, decreasing the average kinetic energy of these particles. When the universe cooled to about 10 to the power of 12 Kelvin, the strong nuclear force, which acts as the glue binding quarks together, overcame the kinetic energy separating them. This force, mediated by particles called gluons, started pulling quarks together to form hadrons. In particular, up and down quarks combined to create protons, 2 up quarks and 1 down quark, and neutrons, 1 up quark and 2 down quarks. This combination of quarks into nucleons marked a significant transition in the matter's state in the universe, from the freely flowing quarks and gluons of the quark-gluon plasma to the formation of matter as we recognize it in the current universe. The Hadron Epoch, therefore, represents a critical phase in the early universe, setting the stage for the subsequent processes like nucleosynthesis, which led to the creation of the first atomic nuclei, and eventually to the formation of atoms, stars, and galaxies. A hadron is a composite particle made up of quarks which are held together by the strong nuclear force mediated by gluons. Classified into 2 major families, baryons and mesons, hadrons are an essential part of the atomic nucleus and, by extension, of all matter as we know it. Baryons, which include protons and neutrons, are hadrons composed of 3 quarks. Protons are made up of 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. Mesons, on the other hand, are composed of 1 quark and 1 antiquark pair and play a role in mediating the strong force between more stable hadrons like protons and neutrons in the nucleus. The strong force, one of the 4 fundamental forces in physics, is incredibly efficient at binding quarks together within hadrons, so much so that quarks are never found isolated in nature, a phenomenon known as quark confinement. This force acts not only to hold the quarks within a single hadron together, but also works between hadrons, keeping the atomic nucleus intact despite the repulsive electromagnetic force between the positively charged protons. The study of hadrons is essential in particle physics, particularly in understanding the strong nuclear force and the behavior of matter under extreme conditions, such as those found in neutron stars or during the first moments of the universe, just after the Big Bang. Experiments in large particle accelerators, like the Large Hadron Collider, LHC, involve colliding hadrons at high speeds to probe the fundamental nature of matter and the forces that govern the universe. Delving into the heart of matter, we uncover the fascinating world of quarks, the elementary particles that serve as the building blocks of the universe. Quarks come together to form hadrons, a process that's foundational to understanding the structure of matter. There are 6 types of quarks, known whimsically as up, down, charm, strange, top, and bottom. The forces that bind quarks together are governed by the strong nuclear force, one of the 4 fundamental forces of nature. This force is mediated by particles called gluons. Hadrons can be classified into 2 main families: baryons, which include protons and neutrons made up of 3 quarks, and mesons, composed of a quark and an antiquark pair. The combination of quarks to form hadrons is not random, but follows specific rules dictated by quantum chromodynamics, the theory that describes the strong force interactions among quarks and gluons. This intricate dance of particles, guided by the laws of physics, shapes the invisible scaffolding of our universe, from the nucleus of an atom to the heart of a neutron star. The distinction between baryons and mesons illuminates the diverse tapestry of particles that compose our universe. At their core, both belong to the family of particles known as hadrons, which are bound states of quarks held together by the strong nuclear force. The difference lies in their composition and the resulting properties they exhibit. Baryons, including familiar particles like protons and neutrons, are made up of 3 quarks. This trio of quarks bestows baryons with a half-integer spin, categorizing them as fermions according to the principles of quantum mechanics. This means they adhere to the Pauli exclusion principle, which prohibits identical fermions from occupying the same quantum state simultaneously. In contrast, mesons are formed by a quark and an antiquark pair. This composition gives mesons an integer spin, classifying them as bosons, which are not subject to the Pauli exclusion principle and can occupy the same quantum state in large numbers. This fundamental difference in their quantum nature underlies many of the distinct roles that baryons and mesons play in the universe. For instance, baryons constitute the majority of the mass of visible matter in the cosmos, forming the atoms that make up stars, planets, and living beings. Mesons, on the other hand, often act as force carriers between particles, playing a crucial role in mediating the strong nuclear force that binds protons and neutrons together in the nucleus of an atom. Their ephemeral existence is typically observed in high-energy environments, such as particle accelerators or cosmic ray interactions in the Earth's atmosphere. The formation of protons, one of the most stable constituents of the universe, is a remarkable process that stems from the principles of quantum chromodynamics. Protons are a type of baryon, composed of 3 quarks, 2 up quarks, and 1 down quark. This particular configuration endows protons with their unique properties, including a positive electric charge. The process of proton formation begins at an incredibly tiny scale within the quantum foam of the universe, where the strong nuclear force, the strongest of the 4 fundamental forces, dominates. This force is mediated by particles known as gluons, which act like the glue holding quarks together. Gluons are exchanged between quarks in a way that is reminiscent of a tether, keeping the quarks within a proton bound together in a perpetual dance. Despite the repulsive electromagnetic force that pushes the like-charged up quarks apart, the strong nuclear force is significantly stronger at the short ranges within a proton, ensuring a stable bound state. It is this intricate interplay of quarks and gluons, governed by the laws of quantum mechanics, that leads to the formation of protons. Once formed, protons exhibit remarkable stability, with a lifetime so long that it exceeds the age of the universe, making them a primary building block of all atomic nuclei. This stability is a cornerstone upon which the structure of matter in the universe is built, from the simplest hydrogen atom, consisting of a single proton and electron, to the complex nuclei that make up the heavy elements. Neutrons share a close kinship with protons, both being baryons composed of quarks, yet they follow a slightly different blueprint. Like protons, neutrons are also made up of 3 quarks, but in their case, the composition includes 1 up quark and 2 down quarks. This subtle difference in quark arrangement gives neutrons their distinct properties, most notably a lack of electric charge, rendering them neutral. The formation of neutrons is a tale of fundamental forces in action, primarily the strong nuclear force facilitated by the exchange of gluons. These gluons act as the adhesive force that binds the quarks together within the neutron, overcoming the repulsive force that would otherwise push the quarks apart. The balance of up and down quarks within neutrons determines their mass and stability, making them slightly more massive but less stable than their proton counterparts under isolated conditions. In the cosmos, neutrons are formed in several astrophysical processes, one of the most prominent being during the supernovae explosions. Here, the intense pressure and energy conditions allow electrons and protons to merge into neutrons, releasing a burst of neutrinos in the process. Additionally, within the nucleus of an atom, protons can transform into neutrons and vice versa through the process of beta decay, a transformation governed by the weak nuclear force. This interplay between protons and neutrons, balancing the forces within the atomic nucleus, is fundamental to the very structure of matter and the endless variety of elements in the universe. The formation and interaction of protons and neutrons play a pivotal role in the architecture of the universe, governing the diversity of matter and the life cycle of stars. At the heart of every atom, protons and neutrons bind together to form nuclei, a process guided by the strong nuclear force. This foundational act of creation underpins the periodic table, determining the type of element and its isotopic variety based on the number of protons and neutrons within the nucleus. In the cosmic furnace of stars, the balance between protons and neutrons is dynamic, driving nuclear fusion processes that power stars and produce the heavier elements essential for life and planetary formation. For instance, in the cores of stars, hydrogen nuclei, protons, fuse to form helium, a process that releases immense amounts of energy and light. As stars evolve, more complex fusion processes occur, requiring and producing neutrons and transmuting elements further up the periodic table. This stellar alchemy culminates in the creation of the heavy elements that make up much of the material world, from the calcium in our bones to the iron in our blood. Moreover, the decay of neutrons into protons, or vice versa, through various forms of beta decay is crucial in determining the stability and abundance of elements in the universe. This decay process also plays a significant role in shaping the energy distribution within the cosmos, influencing the thermal evolution of celestial bodies and the interstellar medium. The dance between protons and neutrons, therefore, weaves a complex web that not only dictates the atomic structure of matter, but also fuels the celestial processes that light up the universe and forge the diverse array of elements that make up our world and beyond. Their continuing interplay is a testament to the delicate balance of forces and particles that shape our understanding of the cosmos. Nuclear fusion is a powerful and fundamental process that occurs at the core of stars, including our Sun, acting as the universe's main energy provider. This remarkable process involves the merging of lighter atomic nuclei, such as hydrogen, to form a heavier nucleus, such as helium. It's a stark contrast to nuclear fission, where heavy nuclei split apart to form lighter ones. The fusion of nuclei releases a tremendous amount of energy, much more so than any chemical reaction could, because it taps into the mass of the nuclei themselves, converting a small fraction of the mass into energy according to Einstein's famous equation E equals mc squared, where E represents energy, m is mass, and c is the speed of light. Fusion occurs when atomic nuclei are brought to extremely high temperatures and pressures, conditions so intense that electrons are stripped away, creating a plasma, a state of matter consisting of free, charged particles. Under these conditions, the repulsive electromagnetic force between positively charged nuclei is overcome by the strong nuclear force as they come extremely close, allowing them to combine or fuse. This process not only powers the stars, but also plays a critical role in the production of nearly all elements heavier than hydrogen in the universe through a variety of fusion reactions. For instance, in the Sun, hydrogen nuclei fuse to form helium in a multi-step process known as the proton-proton chain reaction. In more massive stars, more complex fusion cycles occur, such as the carbon-nitrogen-oxygen cycle, which further contributes to the cosmic abundance of elements. Humanity's quest to harness nuclear fusion on Earth aims to replicate this stellar process, offering the potential for a near-limitless, clean energy source. Despite the technical challenges involved in achieving the necessary conditions for controlled fusion, its successful application would revolutionize energy production, providing a sustainable and environmentally friendly solution to global energy needs. Nuclear fusion in the early universe unfolded in a period known as Big Bang nucleosynthesis, a crucial phase that occurred approximately 3 minutes to 20 minutes after the Big Bang, around 13.8 billion years ago. This epoch was fundamental in shaping the universe's elemental composition as it cooled from an initial state of unfathomably high temperature and density. During the first moments following the Big Bang, the universe was a seething, dense plasma of quarks and gluons. As it expanded, it cooled sufficiently for quarks to combine into protons and neutrons. However, conditions were still too hot for electrons to attach to nuclei, forming a plasma of charged particles. As the universe continued to cool and expand, it reached a critical temperature and density that allowed nuclear fusion to proceed. The first and most crucial fusion process involved protons, hydrogen nuclei, and neutrons coming together to form deuterium, heavy hydrogen, releasing a small amount of energy. This deuterium then served as a sort of building block, fusing with more protons and neutrons to create helium-3 and tritium, hydrogen-3, which in turn could merge to produce helium-4, the most stable and common helium isotope. During Big Bang nucleosynthesis, the rapid expansion and cooling of the universe meant that conditions were right for nuclear fusion for only a brief moment. Despite this, nearly all of the universe's helium was produced during this period, alongside trace amounts of other light elements like deuterium, lithium, and beryllium. The precise ratios of these primordial elements, predicted by theories of Big Bang nucleosynthesis, match remarkably well with astronomical observations, providing strong support for the Big Bang theory. The process of nuclear fusion in the early universe was fundamentally different from stellar fusion in terms of the timescale, conditions, and outcomes. While stars can fuse elements over billions of years, Big Bang nucleosynthesis was a one-time event that occurred in a rapidly changing universal environment, setting the stage for the chemical evolution of the cosmos. In the nascent moments following the Big Bang, protons played a critical role in the orchestration of early nuclear fusion, laying down the foundational elements of the universe as we know it. As remnants from the cooling aftermath of the Big Bang, protons, which are hydrogen nuclei, were abundant and primed to participate in the symphony of creation that unfolded. During the period of Big Bang nucleosynthesis, the universe was dense and hot enough for nuclear fusion to occur, but only for a brief window. In this high-energy backdrop, protons initiated the first step in the chain of reactions that led to the formation of helium, the second most abundant element in the universe. The process began with protons colliding and fusing with neutrons to form deuterium, a heavy isotope of hydrogen, releasing a photon in the process. This initial step was critical. Despite the seemingly simple reaction, the formation of deuterium was a bottleneck in the early universe. Due to the high temperatures, deuterium nuclei were often disrupted by energetic photons before they could participate in further fusion. Once the universe expanded and cooled sufficiently to lower the photon energy below the threshold that could break deuterium apart, the path was clear for subsequent fusion steps. With deuterium as a stepping stone, protons could then further combine with it, progressively building up the universe's initial stock of helium through a series of fusion reactions. This transformative period saw protons at the very heart of cosmic alchemy, driving the synthesis of new nuclei and effectively shaping the elemental composition of the early universe. Thus, the role of protons in early nuclear fusion was foundational, marking the beginning of the universe's transition from a primordial soup of particles to a cosmos filled with a diverse array of elements. Their abundant presence and the simplicity of hydrogen fusion set the stage for the complex chemistry that would eventually give rise to stars, galaxies, and life itself. The formation of the first elements through nuclear fusion, a monumental chapter in cosmic history, occurred shortly after the Big Bang, a cataclysmic event that marked the inception of the universe. As the universe rapidly expanded, it cooled from its initial unimaginably hot state, setting the stage for the first acts of nuclear synthesis. The process began with the simplest element, hydrogen, which predominated in the early universe's elemental soup. Protons, the nuclei of hydrogen atoms, along with neutrons, started to combine under the extreme temperatures and densities of the early universe, forming the first complex nucleus, deuterium, or heavy hydrogen, which consists of one proton and one neutron. The creation of deuterium was a critical step and served as a gateway for further fusion processes. From deuterium, the path to forming helium-4, the next stable nucleus, involved several steps. Deuterium nuclei could fuse with protons to form helium-3, 2 protons and 1 neutron. Subsequently, helium-3 nuclei could collide with each other, merging to produce helium-4 and releasing 2 protons back into the environment to participate in further reactions. This cascade of nuclear fusion transitions didn't stop with helium. Although in much smaller quantities, reactions involving helium and other light nuclei, such as deuterium and helium-3, led to the formation of trace amounts of lithium and beryllium, albeit these heavier nuclei were less favored due to the increasingly energy-demanding reactions and the relative scarcity of suitable reactants. These initial acts of nuclear fusion, occurring in the universe's first few minutes, laid down a primordial mix of elements, predominantly hydrogen and helium, with trace amounts of lithium, beryllium, and perhaps beryllium's subsequent decay products. This elemental distribution set the stage for the later formation of stars, galaxies, and ultimately, the chemical complexity necessary for life. The precise ratios of these primordial elements, dictated by the conditions and laws of physics at play in the early universe, remain observable today in the cosmos's oldest structures, providing a window into the universe's formative moments. Hydrogen's reign as the most abundant element in the universe is a consequence of its simplicity and the conditions present at the birth of the cosmos. Formed in the aftermath of the Big Bang, hydrogen is the simplest and lightest element, consisting of just one proton and an electron. This simplicity made it the first element to emerge as the universe cooled from its initial hot, dense state. During the Big Bang, the universe was a seething cauldron of energy. As it expanded and cooled, elementary particles began to coalesce into protons and neutrons. The universe's cooling allowed these protons and neutrons to begin forming the simplest nuclei, starting with hydrogen. Given the abundance of protons created and the relative simplicity of capturing an electron to form a neutral atom, hydrogen quickly came to dominate the primordial universe's elemental makeup. Additionally, the conditions for creating heavier elements during the Big Bang nucleosynthesis were fleeting, and the process favored the formation of hydrogen and helium, with helium being the next simplest nucleus consisting of 2 protons and usually 2 neutrons. While a small amount of lithium was also produced, the early universe lacked the necessary conditions, specifically the extreme pressures and temperatures found in stars, to foster the formation of heavier elements through nuclear fusion at this stage. This primordial production set the stage for hydrogen's abundance. Stars further cement hydrogen's ubiquity through their life cycle processes. Stars are essentially massive nuclear fusion reactors that fuse hydrogen atoms into helium and eventually into heavier elements in their later stages. However, given that stars begin their lives fusing hydrogen and the vast quantity of hydrogen required to fuel a star over millions to billions of years, hydrogen remains the most prevalent element in the universe. Thus, the simplicity of hydrogen, combined with the conditions of the universe at its inception and the ongoing processes within stars, ensures that hydrogen not only was the first element to populate the universe but also remains the most abundant. The formation of hydrogen, as the universe's most abundant and simplest element, played a foundational role in the development of the cosmos. In the wake of the Big Bang, the universe was primarily a vast expanse of hydrogen gas, interspersed with helium and trace amounts of lithium. This primordial composition set the stage for all subsequent cosmic evolution. Hydrogen's influence on the universe's development is profound and multifaceted. Initially, it served as the raw material for the first stars. Gravitational forces drew clouds of hydrogen gas together, compressing them until the pressures and temperatures in their cores ignited nuclear fusion. These first-generation stars, or population 3 stars, transformed hydrogen into helium and, later in their life cycle, into heavier elements. This process not only illuminated the universe, dispelling the cosmic dark ages, but also seeded the cosmos with the material necessary for the formation of future stars, planets, and, ultimately, life. Moreover, the distribution of hydrogen gas played a key role in the large-scale structure of the universe. Regions of slightly higher density within the nearly uniform early universe attracted more gas through gravity, leading to the formation of galaxies. The vast hydrogen clouds within these nascent galaxies became the nurseries for subsequent generations of stars. Additionally, hydrogen's simplicity and abundance make it a critical marker in understanding the universe's evolution. The absorption and emission spectra of hydrogen provide astronomers with tools to measure the universe's expansion, determine the age of galaxies, and study the formation of stars and planetary systems. Furthermore, hydrogen is central to the existence of life as we know it. Not only is it a key component of water, but the fusion of hydrogen into helium powers the sun, providing the energy essential for life on Earth. The conversion of hydrogen atoms into heavier elements within stars has also furnished the chemical diversity necessary for the complex molecules that constitute living organisms. In essence, the formation of hydrogen laid the groundwork for the complexity and beauty observed in the cosmos today. Its presence fueled the stars that light up the universe, contributed to the assembly of galaxies, and facilitated the creation of the chemical elements that make up the world around us, echoing the significance of hydrogen in the grand cosmic narrative. Hydrogen, as the simplest and most abundant element in the universe, has played an indispensable role in the cosmos's evolution, effectively steering the narrative of the universe from its inception to its current state. Its significance touches upon several key aspects of cosmic development, from the formation of the first stars to the creation of life-supporting planets. Firstly, hydrogen was the initial fuel that powered the universe's first luminaries. The clustering and condensation of primordial hydrogen clouds under gravity's pull led to the birth of the earliest stars. These stars initiated the process of nuclear fusion, converting hydrogen into helium, and in the process, releasing energy that would light up the universe. This transformative era marked a shift from the cosmic dark ages to a lit universe, teeming with stars. Moreover, the fusion processes within stars, beginning with hydrogen, have been the universe's way of forging heavier elements, the building blocks of planets, asteroids, and all known life. As stars age and exhaust their hydrogen supply, they begin to fuse helium into even heavier elements, eventually scattering these elements into space when they die in supernovae explosions. This cosmic recycling and distribution of material have led to the rich, chemically diverse universe we observe today, enabling the formation of rocky planets and complex organic molecules. Hydrogen also serves as a critical tool in astronomy. Its presence and behavior in interstellar space help scientists map the universe, trace the spiral arms of galaxies, and understand the large-scale structure of cosmic matter. The distinctive spectral lines of hydrogen allow astronomers to measure the redshift of distant galaxies, providing evidence for the expanding universe and aiding in the determination of distances across cosmic scales. Furthermore, the abundance of hydrogen in nebulae and protoplanetary disks around young stars is a cornerstone in the formation of solar systems. Hydrogen compounds, such as water, are essential to the development of habitable environments on planets like Earth. The existence of vast quantities of hydrogen in the universe has, therefore, been a precondition for the emergence of life as we know it. In essence, hydrogen isn't just a component of the universe. It has been an active agent in its evolution. From lighting the first stars to serving as the sine qua non for life, hydrogen's role in the cosmos is profound, highlighting its significance in the grand tapestry of the universe's evolution. Antimatter is a fundamental concept in physics, representing a kind of mirror image to the matter that makes up the familiar world around us. Every known type of particle in the universe has an antimatter counterpart. These antimatter particles possess the same mass as their matter counterparts, but bear opposite charges and quantum characteristics. For example, the antimatter partner to the negatively charged electron is the positron, which carries a positive charge. The existence of antimatter was first proposed by physicist Paul Dirac in 1928, arising from his work on quantum mechanics and the theory of relativity. His equations suggested the possibility of particles with negative energy, which at first seemed absurd. However, this prediction was validated in 1932 with the discovery of the positron, marking the first confirmed existence of an antimatter particle. When matter and antimatter come into contact, they annihilate each other in a burst of energy, specifically in the form of high-energy photons or gamma rays. This property underlines one of the greatest mysteries in cosmology, the apparent asymmetry between matter and antimatter in the universe. According to theories, the Big Bang should have produced equal amounts of matter and antimatter, but the visible universe is overwhelmingly composed of matter. The study of antimatter is not just a theoretical pursuit but has practical applications. For example, in medicine, positron emission tomography scans use positrons to help visualize bodily processes. Understanding antimatter also opens potential future technologies, such as antimatter propulsion for spacecraft, which, although speculative and immensely challenging to achieve, would utilize the immense energy released from matter-antimatter annihilation to propel voyages across vast cosmic distances. Antimatter, therefore, represents both a fundamental aspect of particle physics and a frontier of cosmic and technological discovery, embodying some of the most profound mysteries and potentials in the universe. Antimatter differs from matter in several fundamental ways, reflecting what can be thought of as a mirror-image relationship between the two. At the core of this relationship are the contrasting properties that define matter and antimatter particles. This is one of the most fundamental differences. Antimatter particles carry the opposite electric charge of their matter counterparts. For example, whereas an electron, a matter particle, has a negative charge, its antimatter equivalent, the positron, carries a positive charge. Beyond charge, antimatter particles also have opposite values for certain other quantum numbers compared to matter particles. These quantum numbers include properties such as baryon number, lepton number, and strangeness, which are conserved in specific types of particle interactions. Although not yet experimentally confirmed due to the challenges in observing antimatter under gravitational conditions, it is theoretically predicted that antimatter interacts with gravity in the same way as matter. That said, verifying this is a critical goal of modern physics, with experiments like those conducted with anti-hydrogen atoms at the CERN laboratory seeking to shed light on this question. Perhaps the most dramatic difference is what happens when matter and antimatter come into direct contact. They annihilate each other, converting their mass into energy typically in the form of gamma rays. According to Einstein's equation, energy equals mass times the speed of light squared. This process is highly energetic and efficient, starkly contrasting with the interactions of matter particles with themselves, which do not result in such total conversion into energy. The existence of antimatter and its properties raise profound questions about the evolution of the universe. The Big Bang theory suggests matter and antimatter were created in equal amounts. However, the observable universe is dominantly made of matter. Understanding why, known as the matter-antimatter asymmetry problem, remains one of the major unsolved questions in physics. This fundamental difference and the search for answers underscore the rich complexity and the underlying symmetry in the laws of the universe. Matter-antimatter asymmetry, also known as baryon asymmetry, refers to the observed imbalance between matter and antimatter in the universe. Despite theoretical predictions and experimental evidence suggesting that the Big Bang should have produced equal quantities of matter and antimatter, the observable universe is overwhelmingly composed of matter. This discrepancy poses one of the most profound mysteries in physics and cosmology. According to the standard model of particle physics, the behavior of particles and their antiparticles should be nearly identical, with a few subtle differences. However, for the universe to evolve into its current state, dominated by matter, these slight differences must have resulted in processes that favored the abundance of matter over antimatter shortly after the Big Bang. Several mechanisms have been proposed to explain this asymmetry. CP symmetry posits that the laws of physics should remain unchanged if a particle is replaced by its antiparticle, charge conjugation C, and if its spatial coordinates are inverted, parity inversion P. However, experiments have observed violations of CP symmetry in certain weak force interactions, suggesting that under specific conditions, the universe could exhibit a preference for matter over antimatter. Baryogenesis is a theoretical framework that attempts to explain how the early universe underwent a phase that preferentially produced more baryons, particles like protons and neutrons, than antibaryons. This would have resulted in the residual matter that makes up the stars, planets, and galaxies we observe today. Various models of baryogenesis introduce new physics beyond the standard model to account for the necessary CP violation to create this imbalance. Within the hot, dense environment of the early universe, Sphaleron processes could convert baryons and leptons, and their antiparticles, into each other, violating baryon and lepton number conservation under certain conditions. These processes could create a matter-antimatter asymmetry if coupled with CP violating interactions, as suggested in some models of electroweak baryogenesis. Experimental efforts to understand matter-antimatter asymmetry continue in particle accelerators, such as the Large Hadron Collider at CERN, and in observations of the cosmic microwave background and distant galaxies. Solving this puzzle not only would explain the predominance of matter over antimatter, but also would offer profound insights into the conditions and laws that governed the early universe, potentially revealing new physics beyond our current understanding. The mystery of matter-antimatter asymmetry profoundly influenced the formation of protons, a pivotal chapter in the grand narrative of the universe. When the universe was born, it teemed with energy that eventually gave birth to pairs of particles and antiparticles, matter and antimatter. According to prevailing theories, these pairs should have annihilated each other completely, leaving behind a universe devoid of matter. However, the universe we observe today is conspicuously matter-dominated, hinting at an imbalance between matter and antimatter during the early moments after the Big Bang. This asymmetry is believed to have affected the formation of protons, the building blocks of atoms, and ultimately of all matter. For reasons not fully understood, there was a slight surplus of matter particles, including quarks, over their antimatter counterparts. As the universe cooled, quarks clumped together, forming protons and neutrons due to this slight excess. This pivotal process, guided by the strong nuclear force, led to the predominance of matter, allowing protons to survive, bond with electrons, and give rise to the atoms that make up the stars, planets, and life as we know it. Thus, the matter-antimatter asymmetry is a cornerstone of our material existence, influencing not just the formation of protons, but the very fabric of the cosmos. Indeed, there are several compelling theories that scientists have proposed to explain the puzzling matter-antimatter imbalance observed in the universe. One of the leading theories hinges on the concept of CP violation, which suggests that the laws of physics do not apply equally to particles and their antiparticles. This violation could lead to processes where, under certain conditions, matter is produced at a slightly higher rate than antimatter. The theory of CP violation has been partially observed in experiments with certain subatomic particles like kaons and B mesons, offering a tantalizing hint that such imbalances can indeed occur and could have played a role in the early universe. Another intriguing idea is related to the concept of leptogenesis, which posits that the decay of heavy neutrinos in the early universe could create an excess of leptons, a class of particles that includes electrons over antileptons. This lepton asymmetry could then be converted into the baryon asymmetry, the imbalance between matter and antimatter we observe, through processes governed by the electroweak force, one of the fundamental forces in the universe. A third theory explores the possibility of new physics beyond the standard model, involving additional particles or forces that could account for the discrepancy. These hypothetical particles and interactions could have led to processes in the early universe that favored the production of matter over antimatter. Each of these theories attempts to grapple with the enduring mystery of why our universe is made almost entirely of matter. While none of them have been definitively proven, ongoing experiments and observations, including those at particle accelerators and cosmological studies, continue to search for clues that might confirm or refute these theories. The quest to understand the matter-antimatter imbalance not only challenges our understanding of the fundamental forces and particles, but also seeks to unravel the very origins of the universe itself. Dark matter is one of the most intriguing and elusive components of the universe. Despite being invisible and not directly observable by telescopes that detect light or other forms of electromagnetic radiation, dark matter plays a critical role in the cosmos. It constitutes about 25% of the universe's total mass energy density, in stark contrast to ordinary baryonic matter, the matter composing stars, planets, and living organisms, which only makes up about 5%. The term dark signifies that this substance does not emit, absorb, or reflect any form of electromagnetic radiation, making it completely invisible and detectable only through its gravitational effects. The existence of dark matter was first inferred by the Swiss astronomer Fritz Zwicky in the 1930s through observations of the Coma cluster, where he noticed that the galaxies within the cluster were moving much faster than they should be, according to the cluster's visible mass. This suggested the presence of some unseen mass contributing additional gravitational pull. Further evidence for dark matter comes from observations of galaxy rotation curves by Vera Rubin and Kent Ford in the 1970s. They found that stars in galaxies rotate at such speeds that they should fly apart if only visible matter were present, implying the existence of an unseen mass holding them together. Additionally, gravitational lensing, the bending of light from distant objects by massive objects like galaxies and galaxy clusters, provides further proof of dark matter, as the amount of lensing observed is too great to be caused by visible matter alone. The nature of dark matter is one of the biggest mysteries in modern physics. Although we have a good grasp of its presence and the crucial role it plays in the structure and evolution of the universe, such as helping to form and stabilize galaxies, its exact composition remains unknown. Various candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, but as of yet, none have been definitively detected. Understanding dark matter is not only essential for cosmology and the study of the universe's large-scale structure, but also for bridging the gap between known physics and the physics of the unknown universe. Dark matter plays a pivotal role in the formation and evolution of the universe, acting as the invisible scaffolding on which the visible structures we observe are built. Its influence begins in the very early universe and extends throughout cosmic history, shaping the vast cosmic web and the assembly of galaxies and galaxy clusters. After the Big Bang, the universe was a nearly uniform soup of particles, but it contained slight density fluctuations. Dark matter, being unaffected by electromagnetic forces and thus not losing energy through radiation, began to clump together under the influence of gravity in these denser regions. These clumps of dark matter created gravitational wells, areas of stronger gravitational pull that attracted baryonic, ordinary matter. The accumulation of dark matter in the early universe served as the seeds around which gas and dust could gather. As the baryonic matter fell into the gravitational wells created by these dark matter clumps, it began to form the first stars and galaxies. Without the presence of dark matter, the gravitational forces would not have been strong enough to overcome the pressure and temperature of the primordial gas, delaying or even preventing the formation of stars and galaxies as we know them. Moreover, dark matter's influence extends beyond the formation of individual galaxies to the larger-scale structure of the universe. Galaxies are often found in groups and clusters, which, along with gas and dark matter, form massive structures known as galaxy clusters. These clusters are connected by filaments of dark matter and galaxies, creating a cosmic web that spans the entire universe. The distribution and density of dark matter influence the size, shape, and distribution of these structures. In cosmological simulations that incorporate the effects of dark matter, galaxies and galaxy clusters form in a manner consistent with astronomical observations. These simulations show that dark matter's gravitational effects enhance the clumping of matter on all scales, from small galaxies to the vast superclusters and filaments, accurately reproducing the observed structure of the universe. Dark matter acts as the framework around which the observable universe organizes itself. Its gravitational effects are essential for the formation of cosmic structures and for understanding the universe's evolution from a smooth, homogeneous state to the complex and filamentous structure we observe today. The connection between dark matter and proton formation is an element of broader cosmological processes and not a direct linkage in the sense of one directly influencing the formation of the other. Proton formation occurred in the early universe during the first few minutes after the Big Bang in a process known as Big Bang nucleosynthesis, BBN. This epoch saw the universe cool down enough for quarks to combine into protons and neutrons, and subsequently for some of these nucleons to fuse into the nuclei of light elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. Dark matter, on the other hand, is thought to have played a crucial role in the structural evolution of the universe after its initial expansion, particularly in the formation and clustering of galaxies, as it provided the gravitational framework necessary for baryonic matter to coalesce and form into stars and galaxies. Although dark matter does not interact with baryonic matter or itself via the electromagnetic force, its gravitational influence was vital in amplifying the density fluctuations that arose from the early, uniform state of the universe. These fluctuations eventually led to the large-scale structures we observe today. Thus, while dark matter did not have a direct role in the formation of protons per se, it is deeply intertwined with the fate of these protons and other baryonic matter after their formation. After the protons were formed, the gravitational pull of dark matter helped gather them along with electrons and neutrons to form atoms, stars, and ultimately galaxies. This interplay between dark matter and baryonic matter underlies the large-scale structure of the cosmos and dictates the distribution and evolution of galaxies across the universe. The relationship between dark matter and proton, and more broadly atom formation, is more about the context within which these fundamental building blocks ended up contributing to the observable structure of the universe, rather than a direct causal or interactive connection. Modern particle accelerators, such as the Large Hadron Collider, LHC, at CERN, simulate conditions of the early universe on a minuscule scale by recreating the incredibly high energy densities that existed shortly after the Big Bang. This is achieved by accelerating particles to near the speed of light and then colliding them together. These high-energy collisions generate temperatures and energies analogous to those that occurred a fraction of a second after the universe began, albeit within a tiny volume of space. During these collisions, the energies are so high that they mimic the conditions under which the fundamental forces of nature, electromagnetic, weak nuclear, and strong nuclear forces, were unified. Scientists analyzed the debris from these collisions to study a range of particles and forces that played key roles in the early universe, but are not normally observable in the cooler, less dense conditions of the current cosmological era. One of the primary goals of simulating early universe conditions in particle accelerators is to generate and detect quarks and gluons, which are the fundamental constituents of protons and neutrons. Shortly after the Big Bang, the universe was so hot and dense that quarks and gluons existed in a free state, known as a quark-gluon plasma, before cooling and condensing to form protons and neutrons. modern accelerators have successfully created brief instances of quark-gluon plasma, providing valuable insights into the behavior of matter at these extreme conditions. These experiments have the potential to shed light on the nature of dark matter. Although dark matter does not interact with electromagnetic radiation, making it invisible to telescopes, particle accelerators could produce new particles that are candidates for dark matter or provide clues about its properties. By studying the outcome of particle collisions and the conditions that they simulate, scientists hope to answer fundamental questions about the origins of the universe, the nature of its earliest moments, and the laws that governed its evolution. Thus, modern particle accelerators serve as time machines of sorts, enabling researchers to peer back into the high-energy, high-density conditions that existed a mere fraction of a second after the universe's birth, and bringing us closer to understanding its most profound mysteries. It is possible to create protons in a laboratory, primarily through the process of particle collisions within modern particle accelerators. While protons themselves are stable particles that are abundant in the universe, constituting part of the atomic nucleus along with neutrons, creating them in a laboratory setting involves sophisticated high-energy physics experiments. The quest to unravel the mysteries of proton formation is a fascinating journey that engages scientists across various fields, presenting a rich tapestry of challenges and questions. A core puzzle in this realm is the proton's internal structure and the forces that bind its constituents, quarks and gluons, together. Despite being incredibly small, protons pack a complex world inside them, governed by the strong force, one of the four fundamental forces of nature. Scientists rely on quantum chromodynamics to describe these interactions, a theory that is robust, yet notoriously difficult to solve in the case of the low-energy scales relevant to proton formation. Another significant challenge lies in accurately measuring the proton's properties, such as its charge radius. Recent experiments have yielded conflicting results, sparking debates and necessitating more refined experimental and theoretical tools. Furthermore, understanding proton decay, a process predicted by various grand unified theories but not yet observed, poses a formidable challenge. Proton decay would imply that protons are not truly stable but have an immensely long lifetime, leading to implications for the stability of matter and the ultimate fate of the universe. Each of these challenges represents a piece of the complex puzzle of our universe, driving relentless scientific inquiry and technological innovation. The Standard Model of particle physics provides a foundational framework for understanding the universe's fundamental particles and forces, including the formation of protons. At its core, protons are composed of quarks, specifically 2 up quarks and 1 down quark, bound together by the strong force, mediated by particles known as gluons. This interaction is described by a part of the Standard Model known as quantum chromodynamics, QCD. According to QCD, quarks carry a type of charge known as color charge, not related to visible color but named analogously to the primary color's mixing properties. Gluons, the exchange particles of the strong force, hold quarks together by continuously exchanging color charges among them, a process that ensures the quarks are confined within the proton. Despite the immense strength of the strong force at short ranges, it diminishes significantly as quarks come closer, allowing them to form stable associations like protons. This process, however, is complicated by the fact that the strong force is so powerful and the equations describing it are so complex that scientists have to use sophisticated mathematical techniques and powerful computers to study proton formation. While the Standard Model successfully explains many properties of the proton, such as its charge and composition, it remains an area of active research, particularly in understanding how the mass and size of the proton emerge from the dynamics of quarks and gluons. While the Standard Model remains the most accepted framework for understanding particle physics, including proton formation, several theories and hypotheses challenge its completeness and suggest intriguing alternatives or extensions. One significant area of exploration involves supersymmetry, SUSY, a theoretical framework that proposes a partner particle for every particle in the Standard Model. SUSY aims to address several limitations of the Standard Model, including the hierarchy problem and the unification of forces at high energies. If supersymmetry were true, it could drastically change our understanding of proton formation and stability, introducing new particles that could participate in or influence the process. Another interesting avenue is the idea of preons, hypothetical particles that are considered to be subcomponents of quarks and leptons. If such particles exist, they could offer a deeper layer of substructure within protons, challenging the current understanding that quarks are fundamental. This would revolutionize our conception of matter's constitution at its most minute levels. Additionally, theories of quantum gravity, such as loop quantum gravity, LQG, attempt to reconcile quantum mechanics with general relativity, suggesting a quantum description of spacetime itself. Although LQG primarily focuses on the fabric of spacetime and gravitational phenomena, any progress towards a theory of quantum gravity could have profound implications for understanding the forces that govern proton formation. While these theories offer exciting possibilities, it's important to note that they largely remain speculative without definitive experimental evidence to support them. The search for phenomena that cannot be explained by the Standard Model, such as proton decay or anomalies in proton behavior, continues to drive cutting-edge research in particle physics. The pursuit of such discoveries could ultimately lead to a new, more comprehensive theory that encompasses the Standard Model and provides fresh insights into the mysteries of proton formation and beyond. Quantum chromodynamics plays a central role in understanding proton formation, serving as the cornerstone of our comprehension of the strong nuclear force, one of the four fundamental forces of nature. This force is responsible for binding quarks together to form protons and other hadrons, and gluons are the mediators of this force. Unlike electromagnetism, where like charges repel and opposite charges attract, QCD introduces the concept of color charge, bearing no relation to visual colors, to describe how quarks interact. Quarks can carry one of three color charges, and gluons carry color force, making them unlike any other force carrier. The strength of the strong force, as described by QCD, is unique because it becomes stronger as quarks move apart from each other, a property known as confinement. This ensures that quarks are always bound together, preventing them from existing in isolation under normal conditions. When quarks try to separate, the energy of the strong force between them increases until it's energetically favorable for a new quark-antiquark pair to form from the vacuum, ensuring quarks are always contained within hadrons such as protons. At the same time, QCD also explains a phenomenon known as asymptotic freedom, which means that quarks behave almost as free particles when they are extremely close to each other. This dual behavior underpins the stability of the proton, as the quarks are tightly confined but still able to move within it. The challenge with QCD lies in its mathematical complexity. The equations that govern the theory are so formidable that solving them exactly is beyond current capabilities for most physical situations. Researchers rely on numerical simulations performed on supercomputers, a method known as lattice QCD, to study proton formation and investigate the properties of the strong force. Through these efforts, QCD has dramatically advanced our understanding of the internal world of the proton, offering insights into the nature of matter itself. Future experiments aimed at probing the mysteries of proton formation are set to push the boundaries of our current understanding and technological capabilities. These endeavors seek to delve deeper into the heart of matter, testing the predictions of quantum chromodynamics and exploring beyond the Standard Model of particle physics. One of the key experiments in this field is the Electron-Ion Collider, a cutting-edge facility planned to be built at Brookhaven National Laboratory in the United States. The EIC is designed to accelerate electrons and protons, or heavier ions, to near light speeds before colliding them. This will allow scientists to study the quarks and gluons within protons with unprecedented precision, shedding light on how these fundamental particles give rise to the proton's properties, such as its mass and spin. Another significant experiment is the planned upgrade of the Large Hadron Collider, LHC, at CERN, known as the High Luminosity LHC. This upgrade aims to increase the number of collisions that can be achieved, thereby providing a much larger dataset for researchers. With the HL-LHC, physicists hope to observe rare processes and particles that could hint at physics beyond the standard model, potentially offering new insights into the fundamental forces that govern proton formation and stability. In addition to collider experiments, there are ongoing and planned efforts in lattice QCD computations. Thanks to advances in supercomputing, researchers can simulate the conditions and interactions that lead to proton formation on a lattice of space-time points. These simulations are crucial for testing the predictions of QCD in regimes that are challenging to explore experimentally. Together, these experiments represent a multifaceted approach to understanding the proton. By combining high-energy particle collisions, precision measurements, and advanced theoretical computations, scientists are poised to uncover the secrets of proton formation, potentially paving the way for new physics beyond the current models. New discoveries in proton formation have the potential to radically reshape our understanding of the universe. The formation and stability of protons are fundamental to the existence of matter as we know it, underpinning the structure of atoms and consequently all chemical and biological processes. Unraveling the deeper intricacies of proton formation could lead to profound insights spanning from the smallest scales of particle physics to the grand cosmological structures. Firstly, a deeper understanding of the strong force, which holds quarks together within protons, could reveal new aspects of quantum chromodynamics, the theory that currently describes this force. This might lead to an improved understanding of how matter was formed in the early universe following the Big Bang, offering clues about the initial conditions that led to the formation of galaxies, stars, and eventually planetary systems. Additionally, insights into proton decay, a process not yet observed but predicted by several grand unified theories, could dramatically change our view of the universe's ultimate fate. If protons are found to decay, albeit over immensely long timescales, it would imply that all matter as we know it is not eternally stable. This revelation would not only confirm theories that seek to unify the forces of nature, but also introduce a new understanding of the universe's life cycle. Furthermore, advancements in our understanding of proton formation could lead to breakthroughs in technologies based on quantum science and nuclear physics. For instance, better comprehension of the strong force might enhance nuclear fusion research, a promising but challenging approach to generating clean energy. Lastly, such discoveries could potentially identify new particles or forces, offering clues to the dark matter puzzle. Dark matter constitutes a significant portion of the universe's mass, but remains elusive to direct detection. Unveiling particles beyond the standard model involved in proton formation could provide candidates for dark matter or new interactions that shape the structure of the cosmos. Deeper insights into proton formation are not just about understanding a subatomic particle, but could unravel new layers of reality, linking the fabric of the quantum world to the vast expanse of the universe. So, how do you think everything came to be? Did it all start from nothing, or was everything created by something much more advanced than us? Make sure to leave your comments below and subscribe to our channel for more documentaries like this one. Thanks for watching.